Howdy, team. Welcome to the first video about trees. So today we are talking about trees not like trees that exist in nature. These are the synthetic trees of the computer science world. And in order to talk about these, we need to come to some common language. So we're going to start by talking about the tree terminology. So when we talk about trees, we've been talking lately about collections. So, groups of elements. A tree is very similar to a collection. It is a collection, um, and each of the elements is called a node. This is really similar to a linked list, where every element of a linked list is a node. Every element of a tree is a node. Each node may have zero, which is obviously none, no successors, um, or it could have more than that. So, successor, this is a time where their terminology, there are a lot of different ways to say the same thing. So, the idea of a successor or a child or a descendant, all three of those mean the same thing. So in a tree, a node can have zero or more successors. In a linked list, you can have either no successors, which means you're at the very end of the list, or you can have one successor, um, which means that you're somewhere in the middle, at the beginning or at the middle of the list. So we've got nodes, successors, which are also children or descendants. Um, each node can have exactly one predecessor. So predecessor, again, there's different terminology. This could be parent or could be ancestor. So keep that in mind. I'll probably use those terms as well. So each node has exactly one predecessor. That means it can only have one parent, except the starting or top node, um, which is called the root. So the root does not have a parent, and all other nodes will have a parent. So a link from the node to its successor, so from the parent to the child, those links are called edges. And this is because generally when you draw a tree, um, it looks something like this. So these are nodes, and these are edges. Okay. The successors of a node are called its children. Children, descendant, successor. Um, all different words for the same thing. So in what we just drew, these guys are the children or the successors of this guy. And as I mentioned before, the predecessor of a node is called its parent. Nodes that have the same parent are called siblings. So this node and this node are both siblings. And nodes that have no children, so if it does not have any successors, then it is called a leaf because tree, leaf, they're trying to be cute. So these um, child nodes, the one that we were talking about before, they are leaves because they don't have any children. Okay, one last piece of tree terminology is the idea of a subtree. So a subtree is a tree whose root is a child of some given node. So we have, I'm going to draw a different tree, something a little bit bigger. And let's see. Okay, so we have a node and another node and another node and I don't know, something like this. I can choose a subtree from any of these nodes that I choose. So if I choose this node, the subtree starting at this node is this whole tree. The subtree starting at this node that I just colored in is this whole tree. So you can create a subtree from any node. The subtree of a leaf is just a single node. You can create a subtree from any node. This is similar to creating a sublist or a substring. This is how you would make a subtree. Okay, boring terminology. We're getting past it. All right. So the next thing we need to talk about is there's two main types of trees. So the first type that we're going to talk about is a non-binary tree. And my beautiful sketch is disrupting things. Okay, so we have 9 non-binary trees. You can see the idea of it being binary or not binary is the big difference here. So a general tree or a non-binary tree can have, this means that any given node can have any number of children. A binary tree, then, by what you might guess, is a node can have at most 2 children. So a general tree, you can have as many children as you want or need. So in this case, this is a family tree of some of the early English monarchs. Um, and you can see that William the First, he is a node. We have this is a node, this is a node, this is a node. They're just not all drawn out here. But you can imagine this being your own family tree. Maybe you have one sibling, maybe you don't have any siblings, maybe you have 5 siblings. Um, so this allows your nodes to have any number of children. I've already mentioned that. It is fairly uncommon to have a tree that is structured this way. Most of the time, we do use binary trees, which we're about to talk about, but it is possible to have trees with any number of children. Additionally, having this type of tree will help us as we explore the idea of graphs more. Graphs also have nodes and edges, but nodes can have many different edges. So if you think back to what else we've studied that is kind of like this, take a second to think about it. What do you think? All right, it's kind of silly to do that in the video, but I hope you did actually stop to think. We've studied the Java inheritance structure, and we know that it works that way. So at the top, we have object, and below that, we can have a new type. We could have mammal, and below that, we could have giraffe and whale. Um, so it's the same sort of structure that you can have one parent like this. A parent can have more than one child. Maybe we also want human here. This is a general non-binary tree. Okay. Now, let's talk about binary trees. These are the ones that when you're dealing specifically with trees, most of the time you'll be dealing with binary trees, as I mentioned before. So a binary tree has at most 2 non-empty subtrees. So this means that a node is going to have, well, a node is either empty, so any node, either a root node or a leaf node, can be empty. The root it could have two subtrees, and both of those are also binary trees. Um, so notice that this is a recursive definition. So let's talk about that definition with this particular tree. So if let's look at, this is the root that we have access to right now, dog. So we need to make sure that for every node, one of these things is true. So is T empty? In this case, T being our node, no, or being the subtree rooted at that node, the node being dog. Um, it is not empty, but it has two subtrees, cat and wolf, and we need to prove that each of those are binary trees. So then from dog, we're going to go to cat, and cat isn't empty, so we need to make sure that the root of T, or the root, this cat, sorry, each of cat's children are either empty or two subtrees. So in this case, we're going to go again to its left child and say, okay, canine, it is not itself empty, so we need to look at its children. This child here, it is empty. So an empty tree, this one here, it is a empty node. That makes it a binary tree. So it's binary. We're going to now look at the right subchild of canine, this one here. That is empty as well. So that makes it a binary tree. Now we can say that canine is a binary tree because it has two subtrees and both of them are binary trees. Now we go back up to cat, and we have checked cat's left subtree. We have not checked cat's right subtree. So we are going to check here now. This is an empty node, which makes it a binary tree, which means cat is a binary tree. We're going to go back to dog. We still can't answer dog yet. We need to look at its right subtree. So we're going to look at wolf. Wolf is not empty, so we need to check its subtrees or its child trees. So we're going to check this one. It's empty, which makes it a binary tree. Same goes for the right subtree of wolf. So if both of its subtrees are binary trees, we can say, yes, that one is also a binary tree. And now we have proven that both the left subtree and the right subtree of dog are binary trees. So the tree rooted at dog is a binary tree. So the next thing we're going to talk about are a couple more uh, ways to describe trees. So what we're going to talk about are two terms called fullness and completeness. So a tree is full if a tree is sort of perfect looking, kind of like this. So in a full tree, every node has either 0 or 2 non-null children. So here we have every single node. Hold on, where's my pencil? Every single node has 0 or 2 children. This tree here is not full. This tree here has this node, number 5, that has only one child. So this tree is full, and this tree is not full. Okay, now the other term you can see here, fullness and completeness. So when we talk about completeness, a binary tree is complete if all leaves are at either H, so H being the height. So the height of this node, H equals 0. You could start it at 1 if you wanted. Here, H is 1, and here, H is 2. So a binary tree is complete if all leaves are at level H or H minus 1. So the height of this whole tree, we're going to call it 2. These H's that I added here, this is the height of the subtree. So overall, the height of this tree is 2. That means that if we were to call this complete, all leaf nodes are going to be either at height equals 2, which is true for all of these nodes, or at level H minus 1. So at this level. And that is true for this tree that we have been talking about. All of the nodes are either at level H, which is 2, it's going to be at height, or height minus 1, which is 1. Now there is another requirement for completeness, and that is all H1 leaves are on this should be left. Let's scratch it out right here. So all of those nodes are pushed to the left. So this one is pushed all the way to the left. If we're going to have anything empty, it's going to be to the right. See, I am just messing this up again. Let's clear all drawings. So I was thinking when I wrote that before that it was all H leaves are on the right. All H leaves, I'm going to add all level H leaves are to the left. So this means all H minus 1 leaves are to the right. So this doesn't have a child, and so we're saying that it is to the right. It's as far right as possible. So before we reach a H minus 1 level leaf, we will have filled out H minus 1 leaves first. So like before we can add a leaf here, we must have leaves all the way there. I'm not sure I made complete sense there. I hope this makes sense. Let me try to draw another few complete trees. So a tree with just one node, let's see if that is complete. So this has a height of 0, let's say. So that means that this itself is a leaf and all leaves are at level H. It's at 0 and they're to the right. Since there isn't any right or left going on here, we can say that this is a complete tree. Next, let's add another node. Now all leaves are at level H or H minus 1. So this is true. We've got 0 and 1, the height of this tree is 1, so the leaves are either at 1 or at 0, which is true. And then we can say all h minus 1 leaves are to the right, which is true. 0 is to the right. All level H leaves are to the left. True again. Now, if I add another node here, this is no longer a complete tree. So we cannot say that all leaves are at level H or level H minus 1. So the height of this tree is now 2. And we have a leaf node. There's an empty leaf node here. We have an empty leaf node here. And so we have a tree of height 2 with a null subtree on the left, which means that's an empty tree. Um, and that is not allowed because all of the leaves, the non-null leaves, need to be to the left, not to the right. So if instead of adding this new node where I added it, if I added it here, this is now at level 2. What do you think? Is this now a complete tree? No, it's not, because all of the leaves would need to be at level 2 or level 1. And that's not true because we have this null leaf coming off of the node at level 0. So this is not a complete tree. Instead, let's erase this one. Instead, if we add a node here, now we have a complete tree. These both have null subtrees, and all leaf nodes are either at level H or level H minus 1. I hope that makes sense. Um, the way, let me draw one more example. So when you grow a tree for that is complete, you are always drawing from left to right at each level. So I would start by going left and then by going right. And then I would take the leftmost node and draw another left node and then a right node. Then I would find the next node over and draw this way and this way. You can see that I am always keeping my leaf nodes on the lower level and keeping them to the left. On the upper level, I'm keeping them to the right. So I'm going to add another node there and here. I'm maintaining completeness as I draw this tree. Now, as it is right now, this tree is complete. Is it also full? No, it's not. It's not full because we have this node that I'm emphasizing here. It is, it only has one child. Remember, for fullness, each node must have either 0 or 2 children. So if I were to add another child, now this tree is both complete and full. Okay, team, come back for the next video where I give you an example of something that a binary tree is often used for. But until then, have fun. The ending of the video is always really awkward. Forgive. Forgive that. Okay, see you later.